Good morning, students. In the last class, we discussed the various methods of determination of convection heat transfer coefficient, and I told you there are five methods. The first one is the dimensional analysis combined with the experimental data. Second is the exact mathematical solution of boundary layer equations. This we have already done. The third one is the approximate analysis of boundary layer equations by integral method. The fourth one is the analogy between heat and momentum transfer, and the fifth one is the numerical analysis. So today I am going to discuss about the fourth method, that is the analogy between the heat and momentum transfer and dimensional analysis combined with experimental data. So we won't be focusing on the experimental data part, but our focus will be on dimensional analysis only. Okay. So let us see how we can. Yes. So first of all, I'm going to talk about the Reynolds analogy. Uh, we can always have analogy between momentum and heat transfer. So here our focus is to derive a relationship between the heat transfer coefficient and skin friction coefficient. So you remember that heat transfer coefficient is Hx, which is the local one, and skin friction coefficient is Cfx. So we want to derive a relationship between two, and the reason will be clear to you when the final expression is derived actually. Now, whenever we take a surface, so what happens near the surface, the heat transfer is always due to conduction because the fluid is stationary, that because of no slip condition. So what we can do near the surface, we can find the ratio of heat flux to the shear stress in laminar flow. So it is very important to understand that this derivation is being derived for laminar flow. So if we calculate the value of the heat flux, which is given as Qs double dash. So this is the heat flux at the surface. S stands for the surface, and we divide this term here by the shear stress at the surface. So that would be given by, as you know, at the surface, the heat transfer is because of conduction. So I can write minus K dt by dy, where dt by dy shows the variation of temperature in the y direction, divided by mu du by dy. So we can see here this dy and dy cancels out, and here in the next step we have multiplied and divided by Cp. There is a particular reason why we are doing so. So this is the expression that we get. Now, must know that Prandtl number is given by mu Cp by K. So what we can do is, you can see here this term appears here. So that was the particular reason that we have multiplied and divided by Cp. So that is the same equation which I have written on the last page. So I can write now that minus Qs double dash divided by tau s is given by Cp divided by the Prandtl number dt by du. And if we consider that the velocity and thermal boundary layer are identical, that means the Prandtl number is equal to 1. And this situation can exist for fluids like gases. For air is a very good example for this particular case. So I get to the value as Qs double dash divided by tau s is equal to Cp dt by du with a negative sign here. So once again, same equation. Now what I can do is I can separate this dt and du, and here it is d2, it is du on dt. So finally I can integrate this particular equation here. The du can be integrated between 0 to u infinity, because at the surface the velocity of the fluid here would be equal to u is equal to 0, whereas at the boundary layer end it would be equal to u infinity. And similarly, if the temperature at the base or the surface is Ts, whereas the temperature of the free stream, suppose this is the boundary layer, this is the temperature is T infinity. So we can integrate the temperature between Ts to T infinity and U between 0 to U infinity. So this is the expression that we get here. And then we can rearrange these terms. So what I have done here is, this is Qs double dash, Qs double dash, Cp and Cp. And then what I have done, I have multiplied by U infinity and divided by U infinity. Okay. So you can see it here, it becomes u infinity square and it is u infinity. Ts minus T infinity is taken towards the left side and tau s is taken to the right side. So there is a particular purpose for this. So once again, you can see this here. So this u infinity square and is taken towards the right hand side here. So you can see it here, it appears here, and then we also have multiplied here by rho. So rho is multiplied here also. So it is commonly dividing both sides. Now let us see the right hand side expression here. You must remember that Cfx is given as tau s divided by rho u square in rho u infinity square divided by 2, and this is actually equal to Cfx value, and then we get that Cfx by 2 is equal to tau s divided by rho u infinity square. So that means the right hand side of this equation is nothing but Cfx divided by 2. So here we have written it as Cfx divided by 2, and then let us see the Qs double dash. This is the heat flux value. It should be equal to local heat transfer coefficient into the temperature difference, which is given as Ts minus T infinity. So from here I can write Hx will be equal to, that is the local heat transfer will be equal to Qs double dash divided by Ts minus T infinity. So you just see the equation number 3 and equation number 4. This term represents local heat transfer coefficient. So I can write Hx into 1 over rho Cp u infinity is equal to Cfx divided by 2, and Hx divided by rho Cp u infinity is equal to Cfx by 2. Now this is a particular number actually. So here I have given you some glimpse of the previous slide. Okay, I have written the equation number 1 and 2 for your reference only. Okay, now I am coming back to it. Hx divided by rho Cp u infinity. So this number Hx divided by rho Cp u infinity is called the Stanton number. It is written as Stx, and because we are putting x here, so it's a local Stanton number. It is also known as dimensionless heat transfer coefficient, and it can be written now that Stanton number or local Stanton number is equal to, we can also write this local Stanton number as Nusselt number, Reynolds number, and Prandtl number. So basically Stanton number is the ratio of the local Nusselt number divided by the product of Reynolds number into Prandtl number, and that is equal to the Cfx by 2. So this equation which we got right now is known as the Reynolds analogy. And what is the reason that we are representing the heat flux and uh, local skin friction coefficient simultaneously in the form of one equation, which is the Reynolds analogy actually? It is just because uh, the heat transfer can be calculated by measuring the frictional drag on a plate under the conditions in which no heat transfer is involved. So this is very important actually. So what we have done with the help of the Reynolds analogy, we have expressed the relationship between the fluid friction and the heat transfer for laminar flow over a flat plate. And simultaneously, if we know the skin friction coefficient for the flat plate in the laminar flow case, okay, and there is no heat transfer is taking place, even then we are able to calculate the value of the local heat transfer coefficient and the average heat transfer coefficient. So basically, we are just measuring the skin friction coefficient, and with the help of that, we are able to calculate the value of the local heat transfer coefficient as well as the average heat transfer coefficient. So that is the best part of this analogy actually. And one more thing, it is valid for Prandtl number equal to 1. Now there is another analogy which is known as the Chilton-Colburn analogy, and it's important because it is applicable even if the Prandtl number is not equal to 1. So let us see the correlations which we have derived earlier. We derived that Cfx is equal to 0.664 Reynolds number, local Reynolds number raised to power minus 1 by 2. So it can be written in this fashion also. Nusselt number we derived as 0.332, Prandtl number raised to power 1 by 3, local Reynolds number raised to power 1. So what we can do is we can uh, take this Prandtl number towards the left side here and the Reynolds number also. But the Reynolds number, see, we are dividing by, rather I can say we have divided the both sides by Prandtl number raised to power 1 by 3 and Reynolds number or local Reynolds number. So you can see what happens now. So this term will cancel out and here this will cancel out and here we will be getting 1 by 2. So that is what we get here. Nusselt number divided by the Prandtl number raised to power 1 by 3 into local Reynolds number is equal to 0.332 Reynolds number raised to power 1 by 2. So it's a local Reynolds number. Once again, it is the same equation, and if you remember exactly this term, 0.332 into Reynolds number, local Reynolds number raised to power 1 by 2. You can see the previous here, this equation here. So you can see it here. If I divide by 2 here and divide here by 2, so it becomes 0.332. So it is nothing but CFX by 2, and this is Nusselt number, local Nusselt number divided by Prandtl number raised to power 1 by 3 Reynolds number, local Reynolds number. So once again, if you remember the definition of the local Stanton number, it is given by Nusselt number, local Reynolds number, Prandtl number. So I have divided the Prandtl number in two parts. Prandtl number raised to power 1 by 3 and Prandtl number raised to power 2 by 3. So the Stanton number, if I multiply both sides by Prandtl number raised to power 2 by 3, I get Nusselt number divided by the Reynolds number into Prandtl number raised to power 1 by 3. So now you see this particular value and see this particular value. So you can see this particular value is equal to Stanton number into Prandtl number raised to power 2 by 3. So I can say Stanton number into Prandtl number raised to power 2 by 3 is equal to Cfx by 2, and this we get from equations 1 and 2. So this is the Chilton-Coleman analogy, and it is valid for Prandtl numbers varying between 0.5 to 50. Now, there are certain limitations of the Chilton-Coleman analogy, that it is not applicable to heavy oils where the Prandtl number is usually more than 1000, and also for the liquid metals where the Prandtl number is very, very small, which is less than 0.01. And if we calculate the value of the Chilton-Coleman analogy, it reduces to Reynolds analogy. You can see it here in the previous equation. This is the equation. If you take the value of the Prandtl number as 1, this will go. So you will get Stanton number is equal to skin friction coefficient divided by 2. So that means it is giving us the Reynolds analogy. Now, Chilton-Coleman analogy is sometimes written as JH, Stanton number, Prandtl number is to power 2 by 3 CFX 2, where this JH is known as the Coleman factor or J factor for the heat transfer. So it's a sort of you can say the factor which is defined by the scientist himself. This equation is known as also known as the Reynolds analogy. I think yeah, I think okay, it should be for the Reynolds analogy. This equation is also known as Reynolds-Coleman analogy. So okay, this is for the Chilton-Coleman analogy, so we can call it as the Reynolds-Coleman analogy also. It expresses the relationship between fluid friction and the heat transfer for laminar flow over a flat plate, and when the Prandtl number is not equal to 1. The heat transfer coefficient thus could be determined by making the measurements of the frictional drag on a plate under conditions in which no heat transfer is involved. This equation can also be applied to turbulent flow over a flat plate and in a modified way to turbulent flow in a tube. So this is to be seen, but yes, it is applicable to turbulent flow over a flat plate. So that is very, very important point here. It does not apply to laminar tube flow. So it is not applicable to tube flow. That is Reynolds-Coleman analogy is not applicable to tube flow, but it is applicable to turbulent flow over a flat plate and turbulent flow in a tube, but it has to be modified by a certain way that we will discuss later on. So there is a numerical problem. I think this numerical problem, you can pause the video and then see it how we have done it. Okay, it's quite simple. So I am just giving a small pause here, so you can pause your video and see it. Yes, this is the next part. Here I have added one more question. Calculate the drag force exerted on the plate using analogy between fluid friction and heat transfer. So it is basically the extension of the previous question only. So you can see it here. We have used the uh, Chilton Reynolds analogy or Reynolds Colburn analogy and found out the value of the heat transfer. So once again here you can see this and calculate the shear stress, CFX, etc. All these values are given to us. Okay, so I think it's quite easy. Now I am going to discuss about the second method of analysis of the heat transfer coefficient, and that is actually the dimensional analysis method. So I told you I will be discussing about that also. Now, first of all, I am going to discuss the dimensional analysis of forced heat transfer or forced convection actually. Now, when we talk about the forced convection part, there are certain parameters on which the forced convection depends. What are these parameters? The first one is the tube diameter, or you can also call it as some characteristic length. So if it is a flat plate, instead of tube diameter, we will take the length of the plate as the parameter, which we will consider. So you can see here, the symbol is D. You can take it as L also, and its primary dimensions are L. Similarly, the fluid density given as rho, units is kg per meter cube, dimensions are ml minus 3. Fluid viscosity represented as mu, this is the units, and for time we are using the small t, and for temperature we are using the capital T. So there are two things. The next parameter is the fluid velocity, which is given as u infinity. So its dimensions are Lt minus 1. Fluid thermal conductivity, that is Kf, units are watt per meter Kelvin. And if you will find the primary dimensions, you will get this units. Heat transfer coefficient, fluid specific heat, so H and Cp, and these are the dimensions. You can always try to calculate the dimension. It's quite easy, and you have done it in the fluid mechanics course also. And now once we have these number of parameters, 7 number of parameters, if we have lesser number of the parameters, then we can use Rayleigh's method for calculating the relationship between the various parameters. But here the number of parameters are more than 3 or 4. So we can't use the Rayleigh's method of dimensional analysis. So we will go for Buckingham's pi theorem. So you know there are 7 variables and 4 primary dimensions, that is for mass it is m, for length it is L, for temperature it is capital T, and for time it is small t. Therefore, according to Buckingham's pi theorem, the independent dimensionless groups that can be formed are, so we have to form pi groups actually. So it is equal to number of variables affecting the phenomena minus number of primary dimensions. Now what are the number of primary dimensions? These are 4 here, and there are variables are actually 7. So we will get 7 minus 4, which is equal to 3. So we can form 3 pi terms. Pi terms means these are non-dimensional terms. So we can make 3 groups of pi 1, pi 2, and pi 3, in which we need certain repeating variables. I think you remember that we should have 2 types of the flow property, fluid property, and one physical characteristic of the phenomena. So here, physical dimension actually. So here we are considering diameter, we are considering density and viscosity and thermal conductivity as the 4 repeating variables. Okay, and the remaining variables, that is u infinity, Cp, and H, are taken as the non-repeating variables. So this is how we can form the 3 non-dimensional groups pi 1, pi 2, and pi 3, and putting the values of the beings. We are putting diameter raised to power a, rho raised to power b, mu raised to power c, and kf raised to power d. And that is how we can do it for pi 2 and pi 3 also. Now, after doing this, what we can do is we can uh, write the dimensions on the left side and write the dimensions on the right side, and equate the various terms here. Like we have separating the exponents of the dimensional for the dimensional homogeneity. Here we have separated the it for the mass. So the left side it is 0, right side it will be this. So similarly for length, temperature and time. And when we solve this equation for pi 1 term, we get these values of A, B, C, D, and this gives us a dimensionless group which is written as rho d mu u infinity divided by mu, and you know it is a Reynolds number. So pi 1 terms comes out to be Reynolds number. In a similar manner, what I can do, I can go for pi 2 term and I can write all the values, and here you can see, and then I can equate the powers of both sides for mass, length, temperature, and time. And finally, I get this solution, and I get the pi 2 term as mu Cp by Kf, which is actually Prandtl number. And then third pi term is also found, and you can see the third pi term comes out to be Ht by Kf, which is the Nusselt number. So I can say for forced convection, Nusselt number is a function of Reynolds number into Prandtl number. And you know we also got the relationship between the local Nusselt number, which was equal to 0.332 Reynolds number, local Reynolds number raised to power I think 2 by 5, and Prandtl number raised to power 1 by 3. We can check it. It was 4 by 5. If I'm not incorrect. So you can check it. What was the relationship? I will show you also. Uh, just a minute. Yes, it is Reynolds number raised to power 1 by 2. It's not 4 by 5. 4 by 5 is actually used in the Dittus-Boelter equation. So I remember that. So it is 1 by, it is 2 by 3 only, Prandtl number, whereas the Reynolds number is equal to 1 by 2. So similarly, we can do the dimensional analysis for the natural convection. In this particular case, what are the important parameters are? One is the characteristic length, which is LC, primary dimension L, fluid density, fluid viscosity, temperature difference, okay, delta T degree Celsius. So this is written here. Then coefficient of the volumetric expansion, beta, it is T raised to power -1, because beta is the equal to 1 by T, okay, 1 by temperature. Gravitational acceleration, G, fluid thermal conductivity, heat transfer coefficient, and fluid specificity. So you need to remember these parameters. Okay, and these are the dimensions here. You can always define them. So once again, there are 9 variables. So the value of n is equal to 9. But what we can do, we can take the product of 3 things, that is G, beta, and delta T, which represents the buoyancy force. And in case of natural convection, buoyancy force is a very important parameter. So we are considering it as a single variable or one variable. Thus, the variable affecting the natural convection are now remaining only are 7. So basically now we have n is equal to 7 rather than n is equal to 9. So once again we have 4 primary dimensions. So the number of pi terms, as you know, will now be equal to 3. So we can form 3 pi terms. So we have chosen repeating variables as length, characteristic length, density, viscosity, and thermal conductivity. And this is the first non-repeating parameter. This is the second non-repeating parameter, and this is the third non-repeating parameters, and these are the 3 pi terms which we can define. So once again, it's quite simple here. The we have done in case of forced convection, here also we can write the dimensions of the pi terms on the left side as well as the right side and calculate the value of the exponents. So you can see for the first pi term, the values of the exponents are this: a is equal to 3, b is equal to 2, c is equal to -2, and d is equal to 0. And this first pi term that we get is Kirchhoff number. It is equal to G beta delta T LC cube divided by nu square. Nu square is the kinematic viscosity. Nu is equal to mu divided by rho. So this you can do easily. And then we can also express pi 2 term in terms of the dimensions. And here you can see we have calculated the values of E, F, G, H. And then we get it is the pi 2 term, which is the Prandtl number. Similarly, we can find the pi 3 term. Pi 3 term is also quite easy to calculate, where the values of I, J, KL come as this, and this comes out to be the Nusselt number. So we can see that the free convection Nusselt number is a function of Grashof number into Prandtl number. In case of the forced convection, Nusselt number was actually the function of Nod's number and the Prandtl number. But here in case of free convection, Nusselt number is a function of Grashof number and Prandtl number. So only difference between the two phenomena is that in case of forced convection, the Nusselt number is a function of Reynolds number, because Reynolds number is qualifying the type of the flow, whether it is laminar or turbulent. And similarly, in case of free convection, it is the Grashof number which is qualifying whether the flow is laminar or turbulent. So that is what I wanted to teach you today. So you can see this lecture. Once again, if you want to understand the two things, the first one we discussed about the analogy between heat transfer and fluid friction, and secondly we have discussed about the dimensional analysis of the forced convection and the free convection. So you can go through these lectures once again if you want. Thank you.